Alright, here we have Lecture 2 in Unit 1, 1.2, Boolean Logic. Now, Boolean Logic, also known as Boolean Algebra, is essentially the algebra of statements. A statement is a declarative sentence that has a truth value. In other words, it's either true or false. So let's look at this first example right here. And is it a statement? Today is Friday. Yes, that is a statement. 2 plus 3 is 7. That is a statement. More specifically, this is a false statement. Am I Ron Burgundy? No. And no, that's not a statement. That's a question. That has a question mark at the end. It's not a statement. All dogs are vertebrates. That is a statement. True statement. 2 miles north of here. Is that true or false? It doesn't have a truth value. It's an incomplete sentence. That is not a statement. If I said something like 2 miles north of the school there's a Burger King, then yeah, that would be a statement, but that alone is not a statement. So Boolean logic, also known as Boolean algebra, combines multiple statements into a single statement by using a variety of operators. So in standard algebra, we work with numerical variables or numbers. Now we have multiple operations we can apply to those numbers. Those operations include addition, subtraction, division, multiplication, squaring, radicals, so on and so forth. So we can add numbers together, we can subtract numbers, we can multiply numbers, we can divide numbers. What Boolean algebra does is, well, what operations or operators can we apply to statements? Well, we can combine statements with an and statement. All right, we can use or, we can use conditionals, and we'll look at all those later. But for now, know that we can use letters to represent statements. So I can let P represent the statement, I don't know, New York City is our nation's capital, which is a false statement. And I can let Q equal 2 is even, which is a true statement. So we can use letters to represent statements. So like I said, we'll be looking at a variety of operators on these statements, and we will study the following: not, or the negation, and, i.e. the conjunction, or, i.e. the disjunction, and we will also be looking at if then and if and only ifs. So we'll start with not P, which is the negation of P, and the symbol we use to draw that is tilde. So that's the notation we use there. We got P and Q, known as the conjunction. The symbol for that is a kind of chevron looking character there. The conditional, which uses the words if P then Q. So remember, P and Q are statements. So an example of a conditional would be if it is snowing, then it is cold. And we represent that with an arrow. We got the biconditional, which uses the phrase if and only if, and its notation, or it is denoted by a double-sided arrow. I almost forgot. We got P or Q, which is the disjunction, and its notation is the kind of upside-down chevron, or is denoted by an upside-down chevron. So we'll start with the negation. So the negation of a statement P is denoted by that kind of squiggly there. It's the opposite of P. So what the negation does is it will switch the truth value. So if it's a true statement and we negate it, we'll end up with a false statement. If it's a false statement and we negate it, we'll end up with a true statement. So let P represent today is not Monday. So if we want to negate that, then we just remove the word. Today is Monday. And those will have opposite truth values. If P were true, then negated P would have to be false. If P were false, then negated P would have to be true. And let's go ahead and negate Q. So negated Q would be Savannah is not our nation's capital. So by inputting that word not, we negate. So let's go ahead and introduce what we call as truth tables. We'll be doing a lot of work with these truth tables. A truth table outlines all possible truth values for a statement by applying the rules of logic. So let's complete this first truth table here. So if we have a single statement, there's only two possibilities. The statement is either true or it's false. Those are the only possibilities. Well, if P is true, then its negation is false. If P were false, then the negation would be true. So the rule for negation is it just switches the truth value. So that's what a negation does. So negation switches the truth value of a statement. Alright, we're done with negation. Let's move on to the conjunction. Now the conjunction involves and statements, essentially, using the word and. So conjunctions are and statements, essentially. Now, let's go ahead and look at this example. Suppose you must pass math and history to graduate. Circle all circumstances where it's possible to graduate. So number one, suppose you pass math but not history. Not good enough because it says the word and. You've got to have both. What if you take pass history but not math? Again, not good enough. Option 3, you pass both. That means you are eligible to graduate. So we'll circle that one. Or option 4, you do not pass either. Well, that means not good enough for graduation. So the conjunction of statements P, Q, often read P and Q, is only true if both are true. You must satisfy both. Right? If it says you must pass math and history, well, you'd have to satisfy both. And if I tell you that I am 6 foot tall and a professional basketball player, well, I better be both. Otherwise, that would be a false statement. So let's go ahead and complete the table. So if we have two statements, there's 4 possible combinations of truth values. If I have 2 statements P and Q, I can have both are true, both are false, or the first is true and the second is false, or the first is false, the second is true. It's kind of like if you flip 2 coins. If I flip 2 coins, there's 4 possibilities. I can flip 2 coins and get heads on both. I can flip 2 coins and get tails on both. I could flip 2 coins, get heads on the first, tails on the second, or I could get tails on the first, heads on the second. So there's 4 possibilities. So the truth table will just be using the rules of logic P and Q. Well, that's only true if both are true. So looking at this table, I'm going to try and find the row in which both are true, which is the first row. In the first row, they're both true, so the conjunction would be true. And everywhere else, it would be false. And then the negation just means we switch the truth value. So we're negating P and Q, so we just negate everything from the previous column. Switch the false to true, and all the trues to false. So basically an AND statement, if any part of an AND statement is false, the entire statement is false. I.e., it's only true if both are true. Alright, that brings us to the disjunction. In other words, these are the OR statements. Now we need to address a complication in the English language here. There's actually 2 types of OR. What we call the inclusive OR, which means either or both, or the exclusive OR, which means one or the other, but not both. A lot of times in daily communication, we default to the exclusive OR. For example, if you ask your child, hey, do you want McDonald's or Burger King? You mean you can only pick one or the other, but not both. So that's the exclusive OR. Whereas if you're looking at a job application and it says, or better yet, let's look at a math graduation requirement. Suppose you're looking at graduation requirements and it says, in order to get your math gen ed requirement, you need to pass college algebra or quantitative reasoning. Well, then you can, so long as you pass one or the other or both, you're good to go. That's the inclusive OR. So in logic, we default to the inclusive OR. And so the rule for an OR statement is that it's only false if both are false. So let's look at the truth table for an OR statement. So we want to outline all possible truth values. So I can have both of these statements are true. I can have both of these statements are false. I can have the first is true, the second's false, or the first is false, the second's true. That's all possibilities, and now we'll use the rules of logic to finish the table. So the rule for OR is it's only false if both are false. So the only time it's false is if both P and Q are false, which is in the second row right there, and everywhere else it will be true. So basically, in an OR statement, if any part is true, the whole statement is true. So let's look at this example. You must pass college algebra or quantitative reasoning to meet your math gen ed requirement. Circle all circumstances where you meet the math gen ed requirement. So in logic we use the inclusive or. So long as you pass one or the other or both, you're good to go. So if you pass college algebra, good enough. If you pass quantitative reasoning, good enough. If you pass both, good enough. So those are all the circumstances in which you would satisfy that requirement. Let's go ahead and look at conditionals. So a statement of the form if P then Q is a conditional proposition or a conditional statement. So the first statement in a conditional is known as the antecedent. The second statement is known as the consequence. And you want to be careful here, the order does matter. So let's look at a conditional. If Mr. Roberts is elected, then every citizen will get a new car. When would this be a false statement, right? When could you accuse me of lying? Well, it can only be false if I'm elected. So that first part is true. Mr. Roberts is elected, true. But you don't get a car. Alright, so that's the only time, or not everyone gets a new car. That's the only time it will be false. Note that if I'm never elected, if Mr. Roberts is never elected, then the statement is automatically true. And it doesn't matter what follows afterwards. So just a heads up there, the only way it can be false is if the antecedent is true and the consequence is false. So let's look at the truth table. Alright, so, and conditional can only be false if the first part is true and the second part is false. So it's only false in this case if P is true and Q is false. That happens in the second row, which means everywhere else it'll be true. So that's the truth table for a conditional. Let's look at some variations on the conditional. So there's the converse of a conditional. That's where we switch the antecedent and the consequence. There's the inverse, which is where we negate the antecedent and the consequence. And there's the contrapositive, where we switch and negate, basically doing both of those. So let's look at the statement, if it's snowing, then it's cold. And we'll call that statement P. The converse of P just means we flip the antecedent and the consequence. So the converse of if it's snowing, then it's cold would be if it's cold, then it's snowing. The inverse would be negating everything, so if it's not snowing, then it's not cold. And the contrapositive is we flip them and negate. So the contrapositive would be if it's not cold, then it's not snowing. So you flip and negate. So let's go ahead and complete the truth table. So we already got the all possibilities outlined. We're just going to use the straight rules of logic to finish up this truth table. So this first column is negate P. So take everything from the P column and change it. Alright. The next one is negating Q. So take everything from the Q column and change it. Make it opposite. Alright, P implies Q, so this is only false if P is true and Q is false. The first is true and the second is false. So that's going to happen in the second row. Everywhere else it'll be true. Now, the order matters here. Notice I flipped the Q and P, so it's only false if Q is true and P is false. So we want to figure out in what row Q is true but P is false, and that's going to be in the third row. So you can see in the third row, Q is true and P is false, so that's where this would be false. Everywhere else it's true. And then let's look at negated Q, negated P, and negated Q. Again, the conditional will be false. The first part's true and the second part's false. So this time we're looking at the third column and the fourth column, the negations. And we can see in the third row it's false and everywhere else it's true. Now the last one we want to figure out when it's false. It's only false if the first part's true and the second part's false. So we're going to look at the negated Q column first and the negated P column second. And we can see that that is false in the second row, which means everywhere else it's true. Now, here it's where we introduce the definition of logically equivalent. Two statements are logically equivalent if they match in the truth table. Note that these two columns are identical and these two columns are identical. So Q implies P is logically equivalent to negated P implies negated Q. And then we also can see P implies Q is logically equivalent to negated Q implies negated P. In other words, every conditional is logically equivalent to its contrapositive. So every conditional is logically equivalent to its contrapositive. Go back and look at that example with the cold and the snowing. Think about the statement, if it's snowing, then it's cold. I think we can agree that that's a true statement, that, hey, if it's snowing outside, that means it must be below freezing, which means it must be cold. Right? Snowing implies it's cold outside. The contrapositive of that is, if it's not cold, then it's not snowing. That's also true. If we define cold to be below freezing, then not cold means it's above freezing, which means snow wouldn't be possible. Therefore, if it's not cold, it can't be snowing. So that contrapositive is logically equivalent to the original statement. Now note that the converse is not logically equivalent. If it's cold, then it's snowing. That's not necessarily true. There's plenty of cold days when it's not snowing. And the inverse is also not quite correct. It says if it's not snowing, then it's not cold. Again, there's plenty of days when it's cold and not snowing. All right, last page here, biconditionals. So moving towards the end of this lecture. So biconditionals use the phrase if and only if. So P, if and only if Q is known as a biconditional. A biconditional is true as long as both statements have the same truth value. So if the truth values match, then the biconditional is true. The way biconditionals work is essentially means the two statements are interchangeable. So here's an example of a biconditional. 4 is divisible by 2 if and only if 4 is even. Well, that's a true biconditional. Divisible by 2 means the same thing as even. So let's go ahead and do our last truth table of the section. So we go ahead and outline all possible combinations of truth values. So looking at the third column, that's P and Q. Remember the rule for and is only true if both are true. So it's only going to be true in the first row and false everywhere else. The next symbol is or. It's only false if both are false. So P and Q are only both false in the last row. Everywhere else it'll be true. P implies Q. That's only false if the first part's true and the second part's false. We can see that in the second row. So everywhere else it'll be true. And then let's negate P and Q. So P and Q is the third column. So we're going to look at the third column and negate that. So we're going to take everything from the third column, switch the truth value. So true becomes false and false becomes true. And now let's look at the biconditional between P and Q. So we're going to look at column P and column Q, which are the first two columns. Whenever they have matching truth values, the biconditional will be true. So it's true in the first row, false, false, true in the last row because they have the same truth value. All right, last example for the section. Let's look at these two statements. Mr. Roberts is 10 feet tall. That's a false. Oops, not true. I wish that'd be cool if I was 10 feet tall. Not true. That's a false statement. Dogs are mammals. That's a true statement. So once we know the truth value of these statements, the content of the statements is kind of irrelevant. We're just going to use the rules of logic. So P is false. Q is true. So with an OR statement, so long as any part of it is true, then the whole thing is true. So this statement is true. And so P is false, Q is true. So with an AND statement, both have to be true for it to be true. In other words, if any part is false, the whole thing is false. P implies Q, so P is false, Q is true. This is the one people normally trip up on. Remember, the only way a conditional can be false is if the first part's true and the second part is false. That's not what we see here. So this is technically a true statement. It's true vacuously, but it is true. It is a truth by technicality, according to the rules of logic. It goes back to the election. If I make the statement, hey, if you elect me, then I'll get you a new car. If I'm never elected, then technically that's a true statement. You can't ever accuse me of lying. The only way you can accuse me of lying or giving a false statement is if I were elected and I never got you that new car. Alright, so let's look at the negation of P. So if P were false, then its negation will be true. So that's true. And Q is true. So true or true is true. Negation of P is true. Q is true. So an AND statement is only true if both are true. Both of those are true. So that is true. So the negation of Q is false. And P is false. Remember, the only way a conditional can be false is if the first part is true and the second part is false. So this is technically a true statement, even though both statements contained within are false. Again, if I say, hey, if I'm elected, then you'll get a new car. Well, suppose I never get elected and you never get a new car. Can you say that was a false statement? Technically, you can't. It would technically be a true statement. Therefore, you can conclude, at least according to the rules of logic, the only politicians to issue true statements are the ones who were never elected. On that bombshell, we're done with the lecture. You are ready to roll on homework 1.2, so feel free to get started on that assignment and have a wonderful day.